Today, we are going to introduce a new circuit element known as the operational amplifier. Or op amp. Okay. Now, I'm going to switch to a different tab real quick because I want to show you guys what an actual op amp consists of. So this horrifying looking circuit right here, containing 22 transistors, 11 resistors, a diode, and a capacitor, is a simplified version of an op amp. This is a Texas Instruments MU-A741 op amp, a very, very commonly used general purpose operational amplifier. And we can see that it contains 7 terminals. There's a terminal labeled N-, which is the inverting input terminal, a terminal labeled N+, which is the non-inverting input terminal, 2 terminals named offset N1 and 2. Those are for correcting manufacturing errors. We have a VCC plus terminal where we apply a positive power supply voltage, a VCC minus terminal where we apply a negative power supply voltage, and then an output terminal where we measure some sort of output voltage. Okay? Now, the analysis of this circuit is extraordinarily difficult and well beyond what I would ever expect any of you guys to do in this class. Okay? But in a very specific configuration, we can simplify this circuit down to literally just having 2 rules that it will obey. And so that's what we're going to do in this class. And then in circuits 2, for those of you who are crazy enough to be electrical engineers and suffer through that with me, we'll break that down and develop a simplified model that we can use to represent this big thing that isn't quite as simple as the model that we're going to introduce today. Okay. So our schematic representation of an op amp is going to look like this. We represent amplifiers with a triangle symbol. So any amplifier is going to be a triangle because an operational amplifier has 2 inputs. We are going to have 2 input terminals on the left-hand side. So here's 1, here's 2. And typically speaking, one of them in the schematic representation will be associated with a plus sign, and the other will be associated with a minus sign. Now, we may see amplifier circuits where the plus sign is on bottom and the minus sign is on top. That's literally just telling you that those input terminals are switched. It does not in any way, shape, or form change the behavior of the amplifier itself. I like to switch it over on occasion to make circuits easier to draw. That's literally it. Okay. So the input terminal associated with the plus sign is what's called the non-inverting input. And then the input terminal associated with the minus sign is the inverting input. These are named for a very specific reason, which is not going to be really obvious until we get into the meat and potatoes of how these circuits or how these devices are used in circuits. So for now, if it's with the plus sign, it's a non-inverting input. If it's on the minus sign, it's the inverting input. On the right-hand side of the circuit, we are going to have our output terminal, okay? So the operational amplifier takes voltage signals in for its inputs, and it outputs a voltage signal. So this is what would be called a voltage amplifier, because voltage goes in, voltage comes out. There are multiple other types of amplifiers, none of which we're really going to discuss in this class. I just wanted to make you guys aware of that. So when it comes to the circuit analysis that we're going to do in this class, these are our three terminals that we're actually going to pay attention to, okay? I said earlier and showed you that the op-amp is a 7-terminal device. We're going to introduce 2 more terminals here that are not going to show up in our analysis, but are actually extremely important to the behavior of the op-amp. So I want to talk about them real quick. So up here, I'm going to have a terminal for VCC plus, and down here, I'm going to have a terminal for VCC minus. These blue terminals are our power supply terminals. And the reason why they are so important is because an op-amp is what's known as an active device, okay? So resistors, capacitors, and inductors are what are called passive devices because they exhibit resistance, inductance, and capacitance regardless of whether or not you apply any sort of voltage or current signal to them. An op-amp cannot function if you don't supply external power. So that's why we refer to it as an active device. We have to include some sort of external power to this op-amp circuit in order for it to fulfill its role as an amplifier in our circuits, okay? So when we do a lab using op-amps next Wednesday, if you don't, A, remember to make your power supply connections, and B, remember to actually turn the output button on your power supply on, you will not get the desired behavior. Michael, you're shaking your head. You wouldn't believe how many people forget to actually turn it on every damn time. Yeah. So, just to be clear, these 2 terminals labeled in blue, they will never show up in our analysis, but they are critically important to the function of the practical function of the op-amp, okay? So that's why I'm bringing your attention to them. All right, so a little while ago, I alluded to effectively just 2 simple rules that allow us to analyze op-amp circuits, and I'm going to tell you what those rules are now. Rule number 1 is that no current can flow into or out of the input terminals. And I'm going to underline the word input here because that rule very specifically only applies to the input terminals, okay? So current can flow into and out of our power supply terminals. Current can flow into and out of our output terminal, but under ideal conditions, current can only flow, can never flow into or out of our input terminals. Now, the reason for this, which isn't really pertinent to what you're going to learn in this class, but it's kind of an odd thing that we have a section of wire and we're just saying there's no current that could ever flow into them. So the reason for this is what's called the input impedance of the op-amp, okay? So if we look at this guy here, these 22 transistors all have an input impedance. Now, these transistors are what are called bipolar junction or BJT transistors. And the input impedance of a BJT-based operational amplifier is usually on the order of several mega ohms, okay? So 1 to 10 million ohms of resistance is a very large resistance to see. So that any currents that would be flowing through the input terminals of an op-amp during normal operation would typically be of the scale of nanoamperes or picoamperes. So small as to not really affect anything. So that's where op-amp rule number 1 comes in. For a lot of op-amps, they might be based on a MOSFET or metal oxide semiconductor field effect transistor topology. The input resistance of a MOSFET-based op-amp is typically on the order of tera ohms or a million ohms. So the currents in those type of devices are even smaller. So op-amp rule number 1, what it really is saying isn't that no current flows in, it's just that the current is so small as to be negligible for any practical circuit, okay? And we're going to treat that as a current, I could call this, actually I want to use a different color there. I plus is equal to 0, or a current I minus is equal to 0. Our second ideal op-amp rule is that no potential difference can occur across the input term. Now, this particular rule is actually only applicable to what we are going to call a negative feedback circuit. Okay? But in this particular class, every circuit we are going to deal with is a negative feedback circuit. So we can always apply this rule in this class and this class alone. Okay? The reason why this occurs is because negative feedback, what it does is it constrains what's called the voltage gain or the open loop voltage gain of the system. Okay? So an amplifier circuit, its goal is to make the input signal larger. Okay? Well, for a op-amp, the open loop gain is usually somewhere in the order of a few 100,000 volts per volt to a few million volts per volt. And the end user doesn't really get any choice in that. It's set by the manufacturing limits or the manufacturing process, and then it's just going to fall within some range due to small variations in the manufacturing process. Negative feedback allows the end user to use a resistive network to set a very specific closed loop gain. And a consequence of that closed loop gain is that it forces the voltage V plus, which is the voltage present at the non-inverting input terminal, to be almost identical to the voltage V minus present at the inverting input terminal. So we can say that the voltage drop across our input terminals is always 0 volts. These are our two ideal op-amp rules that we are going to use to supplement our knowledge of circuit theory in order to analyze op-amp circuits. So let's begin analyzing some circuits. Notice I'm drawing this one with the inverting input terminal on top, non-inverting input terminal on bottom. I am going to ground my non-inverting input terminal. I'm going to place a 5 kilo ohm resistor here, connecting the inverting input terminal node to the output terminal node. Here's my output. And then at the input here, or specifically the inverting input, I'm going to apply a current source that has a value of 1.5 milliamps. And our goal in this case is simply to determine the output voltage of the amplifier. Okay. Now, before we get into the analysis here, I just want to talk about that negative feedback concept again real quick. That 5 kilo ohm resistor in this circuit is what is applying negative feedback. Anytime we have a conductive path that connects the inverting input terminal to the output terminal of the amplifier, we have negative feedback. That could be a resistor, it could be a wire, it could be a capacitor, it could be an inductor, it could be a voltage source, etc. But whenever there is anything that isn't an open circuit that links the inverting input terminal to the output terminal, we have negative feedback, and we can use those two rules that we described above. As I mentioned previously, every circuit in this class that has an op-amp is going to be that type, but I just wanted to explain what I mean by the concept of negative feedback. Okay, so let's talk about how we are going to analyze these circuits, okay? There are really a couple of different ways that we can approach it. We are going to try to formalize an analysis method that'll get us the right answer, let's call it 99% of the time, okay? So the first step that I want to take, let's do this in blue. So this will be step number 1, is to determine, actually, apply rule number 1 and determine the voltage V plus. So our voltage V plus, and actually all of our voltage is in an op-amp circuit, are traditionally treated as nodal voltages. So V plus represents the voltage present at the non-inverting input terminal with respect to ground, okay? So it would be the voltage measured right here at this node with respect to ground, what would that numerical answer be? 0 volts, because the non-inverting input terminal is tied to ground. All right. While we're at it, I'm simply going to label this current as a reminder that it has to be 0 amps, and label this current as well to remind myself that it has to be 0 amps. Step number 2 is going to be apply rule number 2 to determine V minus, the voltage present at our inverting input node. So this guy right here. So if V plus was 0 volts, what does V minus have to be? 0 volts. So in this case, our inverting input node is effectively serving as what we would call a virtual ground in our circuit, okay? So it isn't actually ground, but it serves that role for effectively the top half of the circuit. Now there are effectively 2 different step 3s in analyzing these circuits. And it depends on what we have in the feedback position, okay? So if we have a voltage source in that feedback path, we're going to apply Kirchhoff's voltage law to determine V out. And if we have literally anything else, we are going to apply Kirchhoff's current law to determine the output voltage. So since we have a resistor in our feedback path by itself, we are going to apply, here's number 3, KCL at the inverting input node and solve for V out. Okay. So let's do it in this gray color. Okay. So I'm going to apply KCL at my inverting input node, which means I'm going to add this current, and this current together, set them equal to 0. Okay. So what's the current directed to the left from the inverting input node? Negative 1.5 milliamps. Okay. What's the current directed to the right? 0. So I'm not going to write that down. I'm just illustrating that that's always going to be there, but that answer is always going to be 0. Now, what about the current flowing up through the 5 kilo ohm resistor? This is where things maybe get a little, let's call it difficult, but not really. Okay. Okay, so there's a couple of different things that are close to right that you guys have mentioned. All right. So Jacob, right? So Jacob, you said that it should be 1.5 milliamps. That's actually correct. Numerically, it will absolutely be 1.5 milliamps because that 1.5 milliamps of current that's flowing into that node, the only way it can flow out is up through that 5 kilo ohm resistor. So numerically, you're 100% correct. But that doesn't give us any information about a relationship with V out. So we're not going to use that simple of a relationship there, okay? Nathaniel, you suggested, I believe, that it should be V out over 5 kilo ohms. I disagree slightly. And the reason why I say that is because the current is flowing into the left-hand side of the 5 kilo ohm resistor to the right-hand side. So if we were applying nodal analysis, which is effectively what we're doing here, we would be assuming that the voltage drop across the 5 kilo ohm resistor would be positive polarity terminal on the left, negative polarity terminal on the right because of the direction that the current is flowing. So I would argue that instead it should be V minus, which in this case happens to be 0, minus V out over 5 kilo. So since V minus is a known quantity, the only unknown variable in this case is V out, which we can easily solve for. And we should get a voltage of negative 7.5, sorry, not milli, volts. By all means, throw that in your calculator and verify it to make sure I haven't made some sort of mistake here. Okay. All right, so I don't want to beat this problem to death too much, but I do want to look at this and introduce two other quick concepts here that'll help in our general analysis of these circuits. So I'm going to draw this resistor here in orange. And I'm just going to call this guy RL, representing some sort of load resistance. So my question to you guys is, would the presence of this load resistance influence the behavior of the circuit at all? Where would it show up in any of our equations if we followed those three steps? Correct. The answer is nowhere. So the presence of a load resistor at the output terminal there, so between the output terminal and ground, will not influence the behavior of an ideal op-amp circuit, except for one very specific case. If that load resistor had a value of 0 ohms or a short circuit, that would make V out be 0 volts. In literally every other case, it has no influence on the behavior of an ideal op-amp circuit. Okay. So effectively, unless we literally force the output voltage to be 0 by directly connecting it to ground, it doesn't matter. What if we put in a resistor right here? I'm just going to call this guy R1. Between the non-inverting input terminal and ground. Would that influence the behavior of the circuit in any way, shape, or form? No, because we know that no current can flow through it, and therefore no voltage drop occurs over it. Okay. All right, good job. You guys are picking up on things quickly. That's wonderful. So let's take our last circuit and make a relatively minor change that will actually influence the behavior quite a bit. Instead of tying my non-inverting input terminal to ground, I'm going to now tie it to a 3-volt source. Let's make this a 2 kilo ohm resistor. This guy a 10 kilo ohm resistor. This guy a 5 milliamp source, like so. And we're going to follow those exact same 3 steps. Okay. So step 1 was to apply op amp rule number 1. So we know that this current is 0 amps and this current is 0 amps. And our goal now is to determine the value of the voltage V plus, the nodal voltage representing the voltage drop, or excuse me, the voltage applied at the non-inverting input terminal with respect to ground. So what's it going to be? +3 or -3? +3. Okay. Step number 2 has us apply op amp rule number 2 and determine the voltage present at the inverting input terminal with respect to ground, which is V minus. What's that going to be? 3 volts, because V plus and V minus have to be the same thing. Step number 3 tells us, because we have a resistor in the feedback path, no voltage sources, we're going to apply Kirchhoff's current law. And so we are going to have consistently -5 milliamps plus V minus, which in this case is 3 volts, minus V out divided by 2 kilo ohms is equal to 0. And then we would solve for V out. So take a moment to do that, please. -7 volts, absolutely correct. All right. Let's work a couple of more problems. So in this problem, I'm going to put a voltage source in the feedback loop, okay? As I mentioned earlier, whenever we have a voltage source in the feedback loop, instead of applying Kirchhoff's current law to solve for V out, we're going to wind up applying Kirchhoff's voltage law. Now, if I'm being honest, I cannot think of any practical application where we would actually put a voltage source in the feedback loop. But the person who wrote your homework problems seems to like to do it. So that's literally the only reason I'm covering it, is because I want you to be able to do the homework. I honestly don't have any clue why you would ever actually do that. So the methodology that I just described, that simple three-step process of applying rule number 1 and determining V plus, applying rule number 2 and determining V minus, and then applying KCL at the inverting input node, will get you through literally any op-amp circuit that I write. So on your exams, in-class assignments, all that kind of good stuff, that's literally all you need to do. But for a couple of weird homework problems, we're going to cover this other thing. Okay. So let's say that I have a 2-volt source like so. A 4-volt source like so. And then here is the out. Okay. So if we apply op-amp rule number 1, we know that these two currents are 0 amps. And our voltage V plus must be 2 volts. Applying op-amp rule number 2, our voltage V minus must be also 2 volts. And so now we're on to step 3, where we're going to apply Kirchhoff's voltage law. Okay. So where I'm going to apply Kirchhoff's voltage law is like this. So I'm going to make some things maybe a little bit more obvious here. Let's do this in orange. So our output voltage, as I mentioned before, all of our voltages here are nodal voltages. So our output voltage is really the voltage measured at the output terminal with respect to ground, which is the same as this voltage. Is everybody okay with that representation? What I'm going to do is I'm going to apply Kirchhoff's voltage law around this loop. So I'm going to start here, go across my input terminals, across my 4-volt source, and then down through my output terminals, right? I can call that a complete loop because I'm starting at ground and I'm ending at ground. So as long as I start at the same potential and end at the same potential, that is a complete KVL path, right? So what do I see? Well, I see the negative polarity terminal of my 2-volt source. So that's negative 2 volts. Then I have the voltage drop across my input terminals, which has to be 0. That's why V plus and V minus are the same thing. So I have, I think I did it in pink. Earlier at the very beginning of class, I just called this voltage drop 0 volts, which is why V plus and V minus are the same thing. So I have negative 2 volts minus 0 plus 4 volts plus V out equals 0. And from this, V out has to be negative 2 volts. So another tricky question here. What if I had done something similar to the first couple of problems where I had a current source connected to the inverting input terminal? Would that change the answer? Not at all. Just means we're going to have some current flowing into the output terminal. Not a big deal. Okay. So it's not going to change the answer in any way, shape, or form. So anytime we have a voltage source in the feedback loop, okay, that is the Kirchhoff's voltage law path I would suggest that you take. It's going to be the easiest one to figure out. Okay. Even if there's a voltage source connected to the, like a voltage source and a resistor or something like that connected to the inverting input terminal, I would still suggest that you take this specific path. Mainly because it most closely aligns with the 3-step procedure that I've tried to introduce to help you guys solve these things systematically. All right, so let's work one more problem. This is more in line with an actual op-amp circuit people could actually use for something. And then I think that'll be enough out of me for the day. All right, so this particular circuit looks like I have increased the difficulty level of this topic several-fold, right? We went from things that looked relatively straightforward and simple to what appears to be an absolute monster of a circuit, okay? This particular circuit would represent a, I would call it medium to hard difficulty problem that I would give you on an exam. And we are going to be able to solve this circuit using those 3 simple steps that I outlined before. Okay? Nothing remotely new is going to be required to analyze this circuit. So what's step one? So we apply rule number one and observe that this current is 0 amps and this current is 0 amps. And our goal now is to find this voltage V plus, which, as a quick reminder, this is always the non-inverting input terminal voltage measured with respect to ground. Is that cool? Any thoughts on how we might solve for that voltage? It is not just 4 volts. 4 volts. You're using the right words there. So since none of the current, let's talk about what's going on here qualitatively real quick, okay? So that 4 volt source, is there a path that current can flow through? Is the 4 volt source going to supply any current? Yeah, okay. Because current that's flowing from the 4 volt source could flow through the 3 kilo ohm resistor and then down through the 1 kilo ohm resistor, right? And that would still satisfy op amp rule number 1. So how much current is the 4 volt source supplying? Exactly right, which would be 1 milliamp. So if there is a current of 1 milliamp leaving the positive polarity terminal of that 4 volt source, what's the voltage drop over the 1 kilo ohm resistor? 1 volt, right? Because 1 milliamp times 1 kilo ohm is 1 volt. The voltage drop over the 1 kilo ohm resistor is the voltage V plus, because it's the voltage measured at that node with respect to ground. So between the non-inverting input terminal node and ground is literally the 1 kilo ohm resistor. So V plus is just the voltage drop over the 1 kilo ohm resistor. Is that okay? Absolutely. You could say, yeah, 4 volts minus 3 volts is equal to 1. Absolutely. It doesn't matter which way you do KVL around there. You're going to get the same answer. Well, I say it doesn't matter. As long as you're doing KVL correctly, you're going to get the same answer. Yes. Okay. So step 1 is taken care of. Are we okay with this? What I have here on the non-inverting input side would be a simple voltage divider circuit is another way that you can think about it. Since we know that no current is going to branch off, the voltage present at our non-inverting input node is just going to be 4 times 1 over 4, which is 1 volt. It's exactly what we observed by determining the current and then using Ohm's law. So you can treat it as a voltage divider circuit, or you can use KCL, KVL, Ohm's law. You're going to get the same result any way that you look at it. All right. So what is our voltage here at the inverted input terminal node? 1 volt. Op amp rule number 2 does not change depending on what other stuff we've got connected, as long as we have negative feedback, okay? All right, so now we're at step 3, where we simply apply Kirchhoff's current law at the inverting input terminal node to solve for V out. So to be clear, that's going to be this current plus this current plus this current plus this current, add them together and make 0. So let's start with the current on the bottom left. So what's the current flowing to the left through the 8 kilo ohm resistor? So 1 volt minus 2 volts over 8 kiloohms, right? We have 1 volt with respect to ground from V minus 2 volts with respect to ground. So that's giving us the voltage drop over the 8 kilo ohm resistor divided by 8 kiloohms. Nothing different than how we would write our KCL equation when we were applying nodal analysis. The voltage at the node we start from minus the voltage at the node we end at divided by the resistor value itself, okay? The current flowing in the bottom right is obviously 0 amps because we've already written it there, so let's move past that one. What's the current flowing to the left through the 2 kilo ohm resistor? 1 volt over 2 kilo ohms. The current flowing to the right through the 6 kilo ohm resistor, 1 volt minus V out over 6 kilo ohms is equal to 0. And from this, we can solve for V out. I get positive 3.25 volts. Did anybody else get that? Okay. All right, so that's enough out of me for today. I don't believe that I uploaded an in-class assignment. That is partially accidental and partially on purpose. So let me explain that really quickly. On Wednesday, we are going to have another lecture on op-amps, wherein I introduce the real purpose of an op-amp, which is to perform mathematical operations on signals. And in that lecture, I'm going to introduce commonly used topologies for amplifier circuits, okay? So we're going to talk about what are called inverting amplifiers, non-inverting amplifiers, buffer amplifiers, integrating amplifiers, differentiating amplifiers, differencing amplifiers, summing amplifiers, all that kind of good stuff. The in-class assignment that I have developed, you can absolutely use just these 3 simple rules and do everything on there. Another way to approach it would be to identify what type of amplifier it is, and then use the rules that we develop next Wednesday. So I'm just going to give you that in-class assignment one time and kind of let you choose your own adventure as to what type of analysis technique that you would choose. I would highly encourage you guys to use the remaining not quite an hour to knock out the homework assignment on op-amp. So homework assignment number 16. It shouldn't take you really more than half an hour to do. It's literally just applying the rules as we've discussed today. And if you do it while you're here, if anything doesn't make sense, you're free to ask me a question. So you can take care of a homework assignment before you get out of here, and then you don't have anything, at least for me, to do over the weekend. So that's what I would suggest. Or since it's ENS day, I don't know, go meet some incoming freshmen or whatever.